Right, the last unit, Unit 13, including part of this lesson, deals with approximations, doing a good job of approximating, function values, things that we just don't understand and we want to have a better understanding of, okay? And we've done approximations before. Back in Unit 5, we used tangent lines to approximate, function values that we don't know, either that will take too long to do by hand or that we just can't do. Take the log of 1.1. I do not know what the log of 1.1 is, but I can I can get a general idea of what the log of 1.1 is using two pieces of information. I can use the fact that I know that the log of 1 is 0. And I know that the derivative of the log function is 1 over x. So that means the slope of the tangent to the log function at 1 over x is 1. Okay, and I create this tangent line. I'm using 1, 0 and my derivative, which was 1, to create my tangent line y minus 0 equals 1 times x minus 1. And that's the equation of this line. Right, well, this is not something that's difficult to work with. This is easy to work with because I can just plug in x values and I would get y values on my line, which I can use to approximate function values on this curve. Okay, so I can use this to approximate f of 1.1. If this is f of x equals log x, can approximate f of 1.1. F of 1.1 is approximately 1 times, now this is a x value. So since this is an x value, I'm plugging this in as an x value into my my tangent line. 1 times 1.1 minus 1, and then plus a 0. This minus 0, if there was anything else, I would add it to the right side, and I just get 0.1. So I think the log of 1.1 is approximately 0.1. Now I can do something even better. Since I know that this is concave down, and I know it's concave down by looking at its second derivative, so y double prime, or d squared y over dx squared, the derivative of 1 over x, either rewriting it as x to the negative first or using the quotient rule as negative 1 over x squared, which is less than 0 for all x's. So that means the log function is always concave down. And for any concave down function, if you're using a tangent line to approximate function values, no matter where your tangent line is located, on the upward slope, the downward slope, it doesn't matter, your tangent line is producing over approximation. So I know this 0.1 is definitely over the actual, as long as my concavity is consistent. And in my calculator, I can go ahead and type in the log of 1.1 to see what the actual value is. And I know it's a little bit under 0.1, 0.095. Not bad. All right. Well, what is the problem with this type of tangent line approximation if I'm trying to approximate log of 1.2 or 1.5 or log of 2? Discuss that with your neighbors. The further you are from your known point, the less accurate your approximation is going to be. Also, concavity plays an important role. The log function is actually concave down, but it's a very slow growing function, and very quickly it starts to flatten out. It will always grow, but the concavity is very slow. So if I had something with a lot of concavity, and let's say it's increasing, but concavity is like that, my tangent line could be way off, even if we are very close, depending on our concavity. Okay, so that's important. If all of a sudden, this was, it just comes up and then goes straight down or something, we could be really far off from our actual. So concavity plays a role too. Well, knowing this, mathematicians decided we need a better job than just one tangent line. And now, this guy, Leonard Euler, is a very famous mathematician. He did a lot in math, discovered a lot of things. He actually discovered the value for E, which is Euler's constant, and it's not lettered because his last name starts with an E. It's just like he already had other constants for A, B, C, and D, and this was the next one. But this one stuck, this E, okay? And Euler decided to ask the question, why are we using one tangent line? Let's use multiple tangent lines. That's what he says. And I hope I'm not, disgracing the name of Euler by doing this. Okay. He said, let's look at this function. This is a different function here. If I use this tangent line to this function with this, extreme concavity, well, my approximation is going to be all the way up here, and it's going to be way off the actual. Tangent approximation, way off. And he's like, don't just use one. Let's use two. Let's use three. Let's use four, depending on how accurate your approximation needs to be. And he first says, okay, well, if you have your known point and you know the slopes of your function at any point, so you know your derivative of your function, and you know what you're trying to approximate, why don't we use steps, okay? And kind of not hip hop, but just like bounce our way from one point to another point and then start again, start fresh. So he says, let's, don't go from this point all the way to this point. Let's just stop here and have this as like a stopping point. And he said, well, you can create this tangent line. I still don't know how to approximate these values, but this point right here is closer to the actual than this point is to the actual. Okay? So why don't we just pause here? And then what he says is assume that that is actually on the function. And knowing the derivative, create a tangent line. So what he does is says, okay, well, what's the slope at this x coordinate on this function? And he kind of looks at dy dx, and he says, okay, that's the slope right there. What we then do is create a tangent line through this point. And he says, great. Now we're kind of hugging along the curve better, and the further we go out, it's not as bad. He then said, okay, well, if you want to take another step, go ahead. If you just want to do two lines, that's fine. Typically, we want our lines to be kind of equally spaced between our origin and what we're trying to approximate. So I'm just going to use one more tangent line, and I have like a step size, a delta x here, and this is delta x, and this is delta x, and that's what we consider our step size. They said, okay, well, let's use to approximate our function value right here. And I know this is going to be closer than, the point up here. And then I'm going to assume that I know what the tangent slope is. Maybe I know the derivative. And I can create another tangent line, assuming that that point is on my function. Okay? Then, using this second tangent line, we produce this approximation, which is going to be closer than my original tangent approximation. We'll call this our approximation using Euler's method, Euler approximation. Okay? Do we kind of visually see what's going on here? We have a tangent line that then hops us to another point, create another tangent line. Maybe it hops us to another point, create a third tangent line. Okay, 3 tangent lines will be very involved. Typically, we'll be asked to, instead of just using 1, use 2. And let's use 2 to approximate the log of 1.1. Let's go back. Don't go back, actually, go forward because I have enough space. But let's go forward and let's approximate the log of 1.1 using Euler's method with a step size of 0.05. So before we say knowing that the log of 1 is 0 and the derivative of the log function is 1 over x, okay? Knowing that I have the point 1, 0, or f of 1 is 0, for f of x equals log x. Okay, knowing that, using the fact that you have 1, 0, if I want to approximate the log of 1.1 with a step size of 0.05, that means I'm going from 1 to 1.1, but I'm going from 1 to 1.05 and from 1.05 to 1. I'm going to use one tangent line at 1 and one tangent line at 1.05. Okay? Compared to our original approximation and to the original value. What do we need to know? Where are we starting from and what we are approximating? In this case, I'm starting from x is 1. I am approximating x is 2. Nope, sorry. I'm approximating x is 1.1. How many line steps are you using? What is the step size? In this case, we're using 2 lines. Our step size is 0.05, which means my first tangent line is going to be at x equals 1. My second will be at x equals 1.05. That one will be used to get to our f of 1.1 approximation. Thanks, guys. All right. So we're using 2 lines, one at 1, one at 1.05 to approximate our function value at 1.1. Each time we take a step, we're going to assume that point is on the original function. And we are going to use the x-coordinate or the x and the y-coordinate to find like what the derivative would be at that point. Okay? Let's see how it looks. I'm going to kind of recreate the picture just so you can see what's going on. Let me draw it up here. Okay, here's the point we know. Here's 1.1. Here's the point we're trying to approximate. Okay, what we're going to do is we're going to create a tangent line at 1. That'll bring us to 1.05. Just flatten this out a little bit. Okay, that'll bring us to 1.05. I will then assume that this point is on the function. I will use the slope of the tangent there, and I will create a second tangent line through that point. And that point, and this second tangent line, I will use to get my better approximation. Okay, here we go. I know for my first tangent line, I have the point 1, 0, and I know that dy dx is 1, and I have y minus 0 equals 1, x minus 1. I will then approximate not f of 1.1, but f of 1.05, which will be 1 times 1.05 minus 1 plus 0, which is just 0.05. Follow me so far? We will then assume that the point 1.05 comma 0.05, my first approximation, which is right here, is on the function. It's on the function. So I will find its tangent slope if it was on the function, which means my dy dx would be 1 over 1.05. So this line's slope is 1.05, or 1 over 1.05. That creates my second tangent line. Y minus 0.05 equals 1 over 1.05, x minus 1.05. Now I can approximate f of 1.1. I get approximately 1 over 1.05 times 1.1 minus 1.05 plus 0.05. Or 1 over 1.05 times 0.5, 0.05 plus 0.05. I know this is going to produce a better approximation than my original tangent line approximation, just using one tangent line. We can go into a calculator and see. This can be done by hand. This is a log of 1.1. Our first approximation was just 0.1. Now I can check what is 1 over 1.05 times 0.05 plus 0.05. And I get 0.0976, which is better than 0.1, comparing that to the log function. Okay? Fantastic. Multiple tangent lines produce better approximations. Now, a lot of the times, though, using this method is not helpful if we have to use our calculator to find our derivative. Like if I were to approximate a square root value, the derivative of root x involves a root. So it's like, well, if I don't know what root of 17 is, and I'm trying to approximate it, I'd have to go and use like the root of 16 and a half, which I can't do. So it's tricky depending on the situation. Typically, what you guys are going to be asked to do on these AP style questions is approximate values of the solution to a differential equation. And this is for a differential equation that you can't solve. You can't find the y equals. Okay? But you'll be given a derivative and you'll be given an initial condition. So here we go. Okay, this is an atypical AP exam question. We got y equals f of x is the solution. That's like misleading because you're not going to be able to find the solution. But they're using this to reference find f of 2. You do know the derivative of your solution. Your derivative is 2x plus y. You cannot solve this differential equation using separation of variables. You also know a point on the original function f of 1 equals 0. What is the approximation for f of 2 obtained by using Euler's method with two steps of equal length starting at x equals 1? Okay, you're figuring out what you're given, what you're being asked to find, how many steps that you're taking. All of that information needs to come here. Okay, you're given the point, you're given the slope. You want two steps. That means two tangent lines. You're starting at 1, you're approximating f of 2. If you're starting at 1, approximating at 2, that means you're going to have two tangent lines, one at x equals 1, and then the next one at x equals 1.5. Right? If you're going from 1 to 2, that's a distance of 1. You have two steps to get there. Well, each step is a length of 0.5. This is our distance divided by 2. Okay? So here we go. Our first tangent line will be at the point that we know. 1, 0, and dy dx, which is 2 times 1 plus 0. And we get our first equation. Y minus 0 equals 2 times x minus 1. Well, I'm going to take my first step and approximate f of 1.5. Okay? Two tangent lines, step size, 0.5. So f of 1.5 will be approximately 2 times 1.5 minus 1 plus a 0. Now, if you notice, always right here inside our x minus x1, this is always our step size. So if we go back to our log approximations, we see like 1.05 minus 1, 0.5. 1.1 minus 1.05, 0.5. Always going to be the step size in there. So that's something to kind of make sure you see every time you're doing these. Okay, and I get 3. 2 times 3 halves. All right, I'm going to assume it is 1. I was thinking 1.5 minus 0. Thank you. I am going to assume that point is on my function. We'll find the slope of the tangent at that point. Now we have 3 plus 1, which is 4. Creating my second tangent line. Y minus 1 equals 4 times x minus 1.5. I'll use that second to approximate f of 2. 4 times 2 minus 1.5, which again is the step size 0.5, plus 1. So 4 times 0.5, that's 2, plus 1, that's 3. It's important to understand kind of the process, understand the picture, rather than memorizing what's going on. A lot of other teachers use a table method, and table methods do work, but a lot of students it's tough to memorize the process of the table. If you think, I'm just using multiple tangent lines, and I'm just working my way over to a better approximation, using different tangent slopes as we work our way over, then hopefully this is just not that bad at all, very easy. See if you can do it. The next one involves some decimals, but try to do it without a calculator, just by hand. Your first stopping point should be at negative 1.6. Make sure your first stopping point is at negative 1.6. In terms of like the y value that you get. Assume that your point, which will be 1.2 negative 1.6, is on your function. Find its tangent slope. Create your second tangent line. And use that to approximate f of 1.4. Okay, approximate f of 1.4. And you should get negative 1.24. Any questions about this? This is a very atypical type of problem. It's a little bit involved. You don't have to show all of the things that I write down. You don't have to write down everything that I write down. But just understand you're using two tangent lines and your step size is 0.2 each time. And just keep track of your arithmetic as well. Okay, the next problem. It's a different type of problem, but it's the same deal. It's actually a little bit easier because you don't have to find dy dx. It's given to you. But it's a little bit harder because, not harder, it's just more involved because you have a step size of 0.2. You have f of negative 0.2, and you're asked to approximate f of 0.4. So you get your tangent line at negative 0.2, go to 0. Then you need a tangent line at 0, go to 0.2. And then you need a third tangent line at 0.2 to go to 0.4. Let's see if we can do that in a reasonable amount of time. got 1.74. Okay, this one, if you have 3 tangent lines, they gave you the slopes, maybe that's the trade-off, but just keep track of things. Shouldn't be that difficult, and if you understand the concept of just use multiple tangent lines, produce an approximation, assume that approximation's on your curve, find the slope of the tangent if that was on the curve, and go from there. All right, any questions at all? Fairly straightforward. Euler's method, there's always a couple problems on the AP exam on Euler's method, always. There's also always a couple problems on logistic differential equations. Now, it's a very one-off topic. Just for some reason, they expect you to know it. On the AB exam, they focus more on exponential growth or exponential decay. This is an exponential growth model, and the population of something just continues to grow and grow and grow and grow, or just will continue to decay. So it trends towards 0. And the key to the growth of something is it's growing dependent on its size. The larger it is, the more it will grow in terms of its quantities. And to write that in terms of a differential equation, you can say the rate of change of a population is relative, so I'll say some constant of relativity, relative to its size. So whatever P is, its growth is dependent on how big it is. The larger P is, the more something will grow. And if you solve this differential equation, you get P equals CE to the KT. This should be an equation that's familiar to you guys, because in physics or in past math classes, you've used this Y equals PE to the RT or PERT before. P equals CE to the RT, or Y equals CE to the RT. There's all different ways that you've seen this. And you can solve this differential equation and you get that. And in my AB calculus class, we kind of focus on specific type of questions that you might see that use this. In this class, though, we don't really worry about exponential growth decay. We worry more about another situation where you can't grow for forever and ever. So populations of certain species on certain parts of the planet. You know, maybe the population of turtles on a Galapagos island. You can't just exponentially grow a turtle population on the island because you don't have enough space for turtles to have millions and millions of turtles on one island. Also, they run out of food. So we can get a certain population, but that's it. You know, we can have a max population, but if we try to go beyond our max, there are certain limitations to having that extra growth, and all of a sudden the ecosystem just fails. Okay, so this is called a logistic growth situation, where we have a carrying capacity or a max population. And that's a y equals L, so L being a population number. And what we see with the graph of something that grows logistically is that we will increase and we will look very similar to an exponential growth curve, but then we get to a point, and at that point our growth starts to slow down and we do not accelerate with our growth anymore. Now, the differential equation for this situation is the following. It's very similar because it's relative to its size, but the max comes into play having this being multiplied by L minus P, where L is the constant. L is our max population. K is also a proportionality constant. If P equals L, dP dt equals 0. You cannot grow if your population gets to your max population. There's another form of this that we need to be familiar with, and it happens by dividing everything by, or multiplying by L over L, and you end up changing this inside to 1 minus P over L. So that's me dividing that by L. But when I multiply this by L, it changes the K, so I'm going to change this to a C so that we don't think it's the same value. Okay, and this would be the solution to this differential equation. And we could go through, just like I could have gone through with the exponential growth and decay, and show you that this is the solution by solving this using separation of variables. But it involves, like, I believe, completing the square and other types of antiderivative techniques that I don't want to get into, and we won't have to use it. So this, not important. I don't want you to, like, erase it, have it, but just know that it's not important, and this is important. And understanding the graph of something that grows logistically looks like this is very important. You will find that all of our questions just deal with understanding what logistic growth looks like and understanding our differential equation for a logistic growth scenario. Now, there could be a situation where you start with a greater than your max population. If you see that and add this in as well, then you will decrease toward your max population like that. Who can think about a situation where that could occur, where we start with something greater than our max population? Ready for this? So you got your Galapagos Island with your turtles. And all of a sudden, a boat shows up with a bunch of turtles. And they're like, here, this is going to be a nice place for you turtles to live. They drop them off. But then all of a sudden, the other turtles who are there are like, no, man, we're maxed out. And so we got all these turtles all fighting for the same food and the same space. Some turtles are going to die. Sorry about your turtles. Maybe I'll use ducks next time. Is that better? Turtles are sad. I know, turtles are endangered on the Galapagos. So I don't know why I picked it. I was thinking islands and turtles. Don't ask me why. Okay? So this might happen. There are key pieces of information that we need to know. That no matter where you start, above or below your carrying capacity, your population will always trend towards your max capacity. Okay? This point right here is a key point on the graph of P. This is the graph of P. Okay? And I could go into the location of this point. It is when our second derivative equals 0, because we can see it's a point of inflection. And if I took this second derivative and set it equal to 0, we would find that this is equal to L over 2. And I'm not going to go into that because it wouldn't give you anything. You could do it. You should take the derivative, set it equal to 0, solve for P, and you'd get L over 2. When your population is L over 2, this is a point of inflection. So we're concave up beforehand and concave down afterwards. Is also the location of the max growth of P. So at L over 2, your population is growing the fastest. Okay, max growth, when is dp dt a max? When its derivative equals 0, that ends up being at a point of inflection for the graph of P. If we know that, we are ready to answer any question that may arise on the AP exam without doing any calculus. As long as we are comfortable with the form of an exponential, of a logistic growth situation, we realize that this L right here stands for its max population, its carrying capacity. If we realize the population will trend towards L no matter where it is, and we realize L over 2 is a key point when our population is L over 2, half of its max. It's a key point, it's a point of inflection. It's when its growth is at a max. We're ready to answer some questions. Population is modeled by a function P that satisfies the logistic differential equation dP over dt equals P over 5 times 1 minus P over 12. If P of 0 is equal to 3, and if P of 0 is equal to 20, what is the limit as t approaches infinity of P of t? Discuss this with your neighbors. If you answered 12, you are correct. 12 is that key point. It is our carrying capacity. It is L. We just look at the differential equation. We see there's 12. That is L. You do not have to do any type of calculus. You do not have to solve this differential equation. You could if you wanted to. It would just take you a long time. We have a situation where we have an initial condition at 3, which is under L, we're still going to trend towards L. We have an initial condition 20, which is over L, we're still going to trend towards L. 12 wins. All right. Part B, discuss this with your neighbors. If P of 0 is equal to 3, for what value of P is the population growing the fastest? This is a free response over this. These are worth like 1 point, 1 point, and then it's like, okay, solve this differential equation, or like, and it like introduces another differential equation and asks you to solve it. So it's one of those things where like, if we know them, these are easy points to get. But if we don't understand the L over 2, or if we forget it, then they're tough. Okay? And there's a lot of stuff to remember for the AP exam. All right, next question. Go ahead and answer this. Discuss this with your neighbors. All right, discuss with your neighbors. A is good. C is good. We have a point of inflection. D is good. We are increasing, or we are concave down when N, our population in this case, is greater than 425. B is not correct. We do not have a maximum value for dN dt when N equals 105, which is at 0. We'd have a very small value. Okay. Next question. This is a legit AP question. Discuss this with your neighbors. Discuss. What'd you get? Which one of these is a logistic differential equation? E. Right? It's relative to its own size, not to time. So this one looks like it's right, but no, that's relative to t, which is time. Its growth is relative to its size. So if this is a y, we need to have y's. There's our L, 5,000, and this is our K. The next question appears difficult, but it's not. Let's read this question. See if we can find an easy answer after doing a little bit of work. How do I find that K? You have a piece of information, you have a P and a dp/dt at a certain time. If you use P and dp/dt at the same time, you can find K. At noon, the population of the roomer is 50 students. So at noon, P equals 50. Also at noon, P is increasing at a rate of 20 students per hour. So at noon, P is 50, and at noon, dp/dt is 20. If you plug in 20 for dp/dt and 50 for P, you can solve for K. That's it. And we know the carrying capacity is 500. It's that simple. Your homework is this take-home quiz. I cannot prevent you from working with others. I will not post the answers, but there are some multiple choice questions. I do not want you to just circle the correct answers. I will be checking over your work, ensuring that you have the proper work for all of your answers. Don't circle an answer unless you have work. We will grade this when we show up, and then we'll get into our next lesson. Our next lesson being the very important introductory lesson to Taylor's series.
That sounds fun.
Used to approximate function values. More approximating function values.
So that's what, like 3 units of approximating?
2 lessons and then a unit.